Hello, everybody. Hello, everybody. Yeah, much better. It's been 3 years since the last one of these in person. It's so awesome to be back with a live audience and a hybrid audience as well at the same time. So for those of you that I haven't seen in 3 years in person, hello again. So this session I've got for you today is called Inside Azure Innovations. And I'll tell you that the really tough part of this session, like in previous versions of this, has been figuring out what to include, which means figuring out what not to include. I had started with a 130-slide presentation. That's how much stuff that I thought would be cool to show, and now it's down to 50 slides, which is not much. It's not much time in 45 minutes to show all of that innovation. So I have to warn you, I'm going to be going through a lot of stuff very quickly. So strap in, lots of demos, and I think lots of really cool innovations. And I'll start just by talking a little bit about the scale that Azure's gotten to, because that kind of underlies the purpose of all our innovation, which is to operate really efficiently at this kind of massive scale. 65 regions, 200 data centers. We're building between 50 and 100 data centers per year at this point, and we see that continuing for the foreseeable future. So massive scale in terms of physical infrastructure, massive scale in terms of service scale as well. And so these are just some of the massive numbers that I thought would be fun to show. There's actually a bizarre number on this slide, because we've passed a threshold on one of these metrics that you could look for. There's a lot of B's and T's, and then there's a Q, which is quintillion. So that's the number of security events we process per month across all Microsoft services, over 1 quintillion, which is 1,000 trillion events. So that's kind of a first for showing kind of scale numbers like this. Now, as far as efficiency of the physical infrastructure, we've been innovating since we started cloud services at Microsoft. You can see here, going back to 1989, Microsoft, and one of the ways we measure the innovation and efficiency of our data centers is using PUE, which is the common industry standard for how efficient the energy output of your data centers are. Energy in versus energy out for IT workloads. And you can see that we've continuously been improving. We're now in the future range where we're starting to deploy these multi-availability and sustainability DCs that achieve their efficiency because they're adiabatically cooled. We get rid of a lot of control equipment. They support both air-cooled as well as liquid-cooled infrastructure. And I'm saying liquid-cooled because that's the way the data center infrastructure is going at Azure. Some of you may have seen us talk about our liquid-cooled infrastructure. But for those of you that haven't, the reason that we're pursuing liquid cooling is when you look at the trend charts here for CPU power consumption and GPU power consumption, you can see that it's just been on this exponential scale. We're at this point now where a typical server is consuming more than 350 watts in our data center. And given air cooling, we just cannot simply pack densely enough the servers with that kind of power consumption. And certainly GPUs, you're kind of restricted with airflow in a data center to only a small number of GPUs in a rack. So this has caused us to go look at how can we pack more densely, which has a bunch of potential benefits, using liquid cooling. So the approaches that we've been looking at include, of course, air-cooled, which is kind of the mainstream right now. We've looked at cold plates, and we will be using cold plates for some of our specialized servers. This is the kind of cooling that I've got in my home system for my overclocked gaming PC, and some of you might as well. But we've been looking at more exotic types of cooling, like single-phase immersion, where we've got a specially engineered fluid, and we put the main board directly in the fluid, and it starts to boil and then evaporates, and then we go back and go through that cycle. But what we found to be really the most efficient way to cool is two-phase liquid immersion, where we actually have a closed tank. We dunk the boards completely in the liquid. The liquid boils, specially engineered fluid, condenses, and goes back down into the tank and goes through that cycle again. And you can see some of the benefits here we get. By putting the main board directly in the liquid, it's not exposed to any corrosive materials. And so we've seen it from our Natick experiment where we put servers in a nitrous oxide environment that we get 1/8 the failure rate of typical air-cooled data centers. We can overclock, just like on our home PCs, up to 20%. And look at that PUE number. And this is what we measured in the Natick underwater data center experiment, a PUE of 1.02. And just for reference, that most efficient data center that we've got coming out that we're deploying right now is 1.11, 1.12. So massive efficiency improvement in PUE. No water in the system, at least any open water that evaporates, and orders of magnitude more efficient than air. And this gives us the ability also to create even smaller data centers because you can see the kind of packing density we get, 2 to 3x the density. So the servers get closer together, the GPUs are closer together, we can pack more, save data center space, which is also great for the environment. So it's all around just a huge win. And we've been experimenting with this now for several years, working on designing our own custom tanks because we can't just go buy the stuff off the shelf. And so here's me going to the lab that we've got here in Seattle. You can see I'm pointing at the temperature, Celsius. It's 114 degrees Fahrenheit, this liquid. This is take number 10, by the way, because I was afraid to put my hand in the tank. But here I did it. You can see it evaporates right off of my hand and drips back into the tank. So that was kind of a scary event. Now, when it comes to the servers themselves and how we operate them, one of the things that we've evolved a long way from the early days of Azure is the way that we update our infrastructure. When Azure first launched, the way we did it is the way that people typically do it. You reboot the server to install anything new on the server. But we'd want to minimize the impact to running workloads when we update our infrastructure. So we've been creating new technologies to update our infrastructure. One of them is called VMFoo, which I've demonstrated before. This is virtual machine preserving host update, where we actually shut down the operating system. You can see the hypervisor and the host OS. We freeze the VMs and then bring up the new operating system and hypervisor and then resume them. And so there's a blip of about 30 seconds. But we've got a whole palette now of choices for updates, depending on the type of update and the constraints that we've got for update. One of them that we've been using now for several years is live migration. Live migration is great. You can update everything because basically you're moving the virtual machine from one server to another. It has some downsides to it. One is brownout time. The workloads get slowed down while you're copying from one to the server. You get a blackout time when you flip from one server to another one. Plus, you need turn space to do it. So it's got some problems. And you need to migrate from one same type of machine to a same type of machine. So we've developed hot patching. So we can hot patch now the host operating system. We can also hot patch the hypervisor now. So these are just applying very targeted fixes to the system. And you can see the update there is very small. And then we've also been working on rebootless, impactless firmware updates for our servers as well, working with industry partners. And so you can see almost all of our firmware updates have no impact at all. But we've just come up with a new technology that gives us another tool in the update toolbox, and that's what we call hypervisor hot restart. This technology is great for updating hypervisor with things that can't be hot patched, like new features, for example. You can't hot patch a new feature. You can hot patch a security fix or a reliability fix, but a whole new feature, you can't hot patch. So we want to be able to deliver new hypervisor features without having to cause a big impact. And you can see with hypervisor hot restart, we're down to less than 1 second. And the way that this works is you've got your existing hypervisor, Hyper-V. You bring up a new one side by side on the same hardware. You transfer state from one to the other, and then you shut down the old one. And this has a blackout time in the hundreds of milliseconds. So let's see that demo of that in action. And so what I've got here are 4 virtual machines. We're pinging each of these 4 virtual machines on a server that on the left side here, we're going to run the hypervisor hot restart script. And that script now is doing exactly what I just showed you. And you can see here on the side, you can see the pings go from low milliseconds up into the couple hundred milliseconds across all of them. And so that is what we just did, and that there's a different order of ICMP there, which is why you didn't see it. We've completely updated the new hypervisor live underneath those 4 virtual machines with only a modest increase in the latency of ICMP pings to those. So that is a new tool, and we've already done a fleet upgrade with this technology. So it's fleshing out our palette with, and we continue to evolve and, by the way, innovate on all of these to bring down these impact numbers to even lower numbers. So speaking of our servers, one of the things that we're doing with our servers is pulling them apart. And by pulling them apart, I mean going from this traditional IT infrastructure, which we started with Azure, which is you're running I/O for the virtual machines completely inside of the servers themselves, consuming CPU resources of the server, burning a lot of CPU actually, because you're doing all of this I/O network processing in CPU cores. And we've been migrating. Some of you have seen me talk before about our accelerated networking, where we offload to a separate card and running an FPGA our network data path. But we've been evolving a lot in this direction of offloading everything. So not just networking, but also storage I/Os. And this is something new now. We've got storage and network offloads going to an FPGA. Not just that, but we've revamped the architecture of our offload, which was before just the FPGA, just the network data plane, to bring a control plane onto that as well. So we've got a system on a chip running Mariner Linux. So now the offload control plane is running Linux. So the agents for the server are all running there on the Mariner Linux on the SoC. And the data plane is implemented in FPGA just like our accelerated networking, though this time we've gone a step further with the accelerated network even. The whole network adapter is in the FPGA. So rather than an ASIC from a third party, we're controlling the network adapter technology in programmable hardware, the FPGA. And this is also where we've got our storage data plane offload implemented as well. And that network adapter is using RDMA. So all of our traffic inside of our infrastructure network is RDMA traffic, even across data centers. And this is what the board looks like. There, you can see the SoC there is on the left side, the network the FPGA there is on the, the FPGA is under the fan, the SoC is under those fins, and then you can see on the left side the network ports in and out. And this has given us a big boost in performance. So earlier this year, we introduced EBS v5 virtual machines, which are a big jump up in performance off of the previous generation of the E-series, V4s. And we're now going to be introducing a new version of the EBS v5s with 96 and 114 cores that have even more performance. You can see 2x the storage performance than the previous E5 series, and 6x storage performance from the previous one. And that is because of this storage offload. And so let's go see a demo of that really quickly. So I've got Iometer here on the left, which is the EBS v5 previous version, and Iometer on the right side, which is the new one with the storage offload. And we're going to run this thing with 100% random read I/O to see how many IOPS we can get off this thing. And so you can see we get about 125,000 off of the previous one, and like I said, 2x over 260,000 IOPS on the right side, all with storage offload. And then here, if we take a look and see what the storage bandwidth is going to be off of this, comparing the old one with a tool called FIO and the new V5 type, you can see we're getting about 4 gigabytes per second of storage bandwidth, and then close to 8 on the right side. So again, double the bandwidth, double the IOPS, all because of that big storage offload re-architecture that we've got with accelerated offload. And again, we continue to evolve that to even get more efficient and get bigger, higher speeds and feeds. This pulling apart of the server goes even further. We're pulling apart and stretching servers across the data center as well. And one of the places we're doing that is with accelerated networking. So one of the things that we don't want to do is load up these server cards with all of the hardware required to run the most workload-intensive applications. What I mean is that most VMs, most VM types, we offer with the kind of general purpose speeds and feeds for storage and network I/O. But there's some virtual machines that need extreme performance. And we don't want to put that extreme performance offload card in every single server because not every single server needs it. So one of the things we're doing is offloading what we call our performers to appliances. And the first place we're doing that is with networking, where we're offloading network performers that need high connections per second from the overlay card. The kind of workloads that need that are network virtual appliances. They're often have millions of connections coming and going to the VMs that are behind the network virtual appliance. And so those are what we call performance. And the way we're going to handle those, rather than putting massive accelerated offload cards in each server, is putting them behind this Sirius appliance. And the Sirius appliance there, then, is where the network traffic gets routed off of the accelerated offload cards, where that's where the SDN processing happens. And that's, these appliances have a lot of these accelerated offload cards sitting inside them, so they can process tons of requests, much more than the local offload card. So let's go see a demo of that in action. And here on the right side, I'm starting up a server. This is NTT-TCP, where we're going to be looking at the stats. We're going to start the traffic there for the server. Now we're going to start the client. And what you're going to see in the metrics here on the upper left, as we push the thing to its limit, and it goes to the Sirius appliance, is 1.5 million connections per second. Significantly higher than what we get off of the local accelerated offload card, and what network virtual appliances need. Feel free to clap at any time. So another place that we're offloading really is in offloading block storage. And one of the challenges that we've had with customers that are coming from on-premises where they've got SANs is, hey, they want SAN performance and management in the public cloud. And we've been lacking that. We've got great high-performing disks, but it's hard to put them together in a SAN configuration where you're getting the kind of IOPS off them that you get off your local SANs. So we announced yesterday on Satya's keynote Azure Elastic SAN. And Azure Elastic SAN provides you SAN-like capability in the public cloud with all of public cloud features around it, including management and governance and network security group rules. You can see we've got the same kind of constructs and object model that you'd have with SANs on premises of a volume group with a bunch of volumes behind it. The difference here is that rather than having local SSDs behind those volume groups, we actually have Azure storage behind those volume groups, those volumes. And what we do to get high performance out of Azure storage block devices, virtual block devices here, is stripe across a bunch of Azure storage block devices. And all of that's hidden behind the volume abstraction here, which is presented as a SAN. In fact, we also go so far as to have iSCSI interfaces projected into the virtual machines so that the typical SAN-type workloads continue to work with easy migration from on-premises. And so let's go see a demo of Elastic SAN. Here I've got a bunch of volumes in a volume group. And we're just going to run against one of them, Iometer, and you can see I'm getting about 250,000 requests per second. Here I've got 6 virtual machines hitting that volume group. And if you add that up, you can see each one is 100 to 200,000 IOPS. The total sum comes to over 1 million IOPS. This is about 1.2 million IOPS you're seeing being executed right in front of you off that Elastic SAN, again, using SAN-type constructs. So now we finally have this path for people to take their on-premises SAN infrastructure and easily lift and shift it into the public cloud. So, yeah. I'll pause as long as you want for the, okay, I guess that's enough. Now, the future of infrastructure is actually containerization. So we've been talking about virtual machines, and I talked earlier about virtual machines and the updates that we've got under those virtual machines. But where the cloud is going and where most enterprises are going with their workloads is containerizing them. And not just containerizing them, but going to serverless containerization. We strongly believe that's the future, that people don't want to worry about managing container orchestrators. They really want to focus on applications and be able to define an application and then with the container specs and just give that to the public cloud and have us take advantage of it. A great example of a workload that is already serverless container enabled is Azure Functions. So Functions as a service going to containerization. Now, one of the things that we want to do with our Azure Container Instances, ACI service, is really make it a no-excuse solution for workloads that need containers. And one of the things that we see in cases like Azure Functions is the need to be able to create lots of containers very quickly. So some of our customer workloads are very bursty. Spin up to 1,000 instances, come back down to 500. Then later in the day, come back to scale to 0, and then go back up and scale to 10,000. So we need to be able to create thousands and thousands of these lightweight instances. And that's kind of the key difference between a virtual machine and a container, is that you can, with a container, spin up much more in a much more lightweight manner, and that means the workloads want to use that to get much more fine-grained, which means that they're going to need a lot lower latency and a lot higher throughput as they create them. It's not like a virtual machine where you launch it and you let it run for a few days. Here you run this thing maybe a few seconds or minutes. So with Azure Container Instances, where you can define these container groups, what we've been working on is how can we make it so that we can deliver that kind of performance. When you talk about the path today, the unoptimized path, which we continue to work on to make more efficient, creating a container group takes a few minutes, or creating lots of instances of a container group. Take the example of 30, 500, 1,000 container instances. You're going to be waiting a few minutes to spin those up. And one of the reasons, of course, is that you need to bring down images, you need to fire up those images to get them running. So we've been working on warm pooling technologies to make that faster. And with warm pooling, what we do is pre-warm containers. And there's different types of warm pooling that are possible. One of them is just, let's have the images cached on the servers so that they're ready to go. All the way to, you've actually got containers up and running, and they're just sitting there waiting for somebody to activate them. And so that is kind of the hot warm pool. And depending on what the needs are, what the customer is going to pay for, and even us behind the scenes looking at the workloads and saying, oh, this workload is very bursty, so let's go ahead and create a warm pool for it so that when they start to fire up and scale out, that they get great performance, and that's all done transparently. So either manual knobs all the way to transparent knobs that are driven by AI watching workloads' behavior and predicting what's going to happen next. Let's go see a demo of warm pooling in action. And what I'm going to do in this demo is compare the cold path with the warm path today on ACI using Azure Functions. So we're going to spin up 1,000 container instances. On the left side, cold path. On the right side, warm path. And you can see I've already started to spin them up. And I'm refreshing on the right side. You can see we're getting hundreds of containers spinning up. On the left side, if we go and refresh here, you see that we still only just have a few containers that have spun up. And that's actually, like I said, going to take a couple minutes for all those 1,000 to show up on the left side. On the right side, just to show you that these are really live running containers already, we're going to pick one. We're going to get its IP address, go to it, and it's an Azure function, like I said, and then you can see the Azure function is up and running. We can even SSH into it and take a look around. A live container instance up and running. So 1,000 container instances you can see in just a few seconds with warm pooling technology. And this is not yet deployed, it's coming. So I just wanted to emphasize that. A lot of what I'm showing you is not yet out yet, so it's coming. All right, the next thing I'm going to talk about is confidential computing. So confidential computing, we think, is the future of computing. It's not a specialized type of computing. Today, we call it confidential computing. In the future, it'll just be computing. So what is the idea behind confidential computing? Well, if you take a look at the way security has evolved for computing, it's gone through evolutions. One of the first places where we decided we need to encrypt and protect data is at rest. And so we've got encryption at rest, and you can see public clouds like Azure now have server-side encryption with server keys, customer-managed keys with encryption on top of that where the customer controls the keys. That is just kind of bread and butter now for enterprises' workloads coming to the public cloud as they want to protect their data while it's at rest. We've also seen the evolution of protecting data while it's in transit. So as people are hitting websites, you're not going to port 80 anymore. You're going to an SSL port with TLS on it because you want your traffic protected and you want a cert to know which service you're talking to. That is just table stakes now. The whole world is using SSL. What's been missing, though, is protecting the data while it's in use. And this is kind of something that I've been personally involved with back when I first started in Azure and heard about this technology called Trusted Execution Enclaves. With Trusted Execution Enclaves, you can protect the data while it's in use. This is hardware that creates an enclave or environment that is like a black box. And it's got some cool properties to it. One is that it encrypts the memory around the black box. And it makes it so that the only things allowed to see what's inside the box are the things inside the box. Anything outside, the hypervisor, the host operating system, an administrator on the machine, can't get in to see what's in that memory. It's got a second property, which is that it measures what's in the box. And then it produces what's called an attestation, which is a report. Here's what's in the box. And it signs it with the hardware, which has a secret key. So that somebody that gets that attestation, which is signed by the hardware, can look at it and say, the hardware says this is the code that's inside this enclave, inside this black box, and they can decide whether they trust that code or not, and the code and the policies that it's implementing. And the way they do that is by looking at the hash of the code and the hash of the policy. And they compare that with the hashes that they trust. If they trust those hashes, then they can release data to it, encrypted, of course, over the wire, and say, here, compute that's inside this black box, I'm going to share some data with you. You can go do analytics, processing, machine learning, whatever on it. And I know that nothing else is going to be able to see that data. Again, the cloud provider can't see it. Malicious insiders can't see it. Hackers that get in the infrastructure can't see it. It's completely protected with confidential computing. One of the ways that we've been leading this is we co-founded the Confidential Computing Consortium. We were the first to bring confidential virtual machines out to the public cloud with SGX technology. And earlier this year, two big milestones in confidential computing that we were at the forefront with our hardware partners is the first to bring out confidential virtual machine technology with AMD SNP technology. Because SGX creates what are called enclaves, which are basically black boxes inside of a process, which means you've got to re-architect your code to say this part's outside, this part's inside. But with confidential virtual machine technology, you can run a full-blown operating system inside the enclave. And that makes it really easy to lift and shift code and applications into confidentiality. It also supports confidential containers, too, because confidential containers with strong isolation of a hypervisor is effectively a lightweight virtual machine. And then the second big breakthrough that we had earlier this year is announcing with AMD the first confidential GPUs. Kind of a missing piece in the whole confidentiality hardware story was, okay, so you've got your confidential hardware with your CPU. That's great for CPU-type workloads. But what about GPUs? What about AI, ML, HPC? How do you protect that? Now you can, coming with these confidential GPUs. And the whole industry is rallied behind confidentiality, so you're seeing confidential hardware come out from all of the hardware vendors. So big steps happening in the maturation of confidential computing, including in the software space, like I mentioned, confidential virtual machines, confidential containers we've got, confidential pods for Kubernetes. More is coming out, confidential SQL on confidential virtual machines, confidential AVD now that we've announced here at Ignite. But one of the things that we're also doing is making it easy for customers to consume this. And one of the scenarios that we hear about a lot is, I want to protect my data as I give it to an ML model. And I might also want to protect the ML model. The producer of the ML model wants to protect it. So I've got a demo just to highlight here that scenario of, I'm going to provide some data to the public cloud. I don't want the public cloud to see it, but I want an answer back about what the ML model is going to say about this data. And similarly, you can imagine whoever created this model wants to protect it from the public cloud as well and from anybody else that might get access, unauthorized access. So in this demo, you're going to see here is we've got an SMP virtual machine running a confidential ACI container. That confidential ACI container instance has 3 images inside of it. One of them is a Triton inference server off the shelf. Another one is encrypted storage sidecar. What that does is it pulls in an encrypted model that it only can decrypt if it passes a security policy that says, this is my code footprint, again, like I mentioned, with an attestation that will allow the release of the key to decrypt the model. And then finally, a network proxy with a tested TLS that will only connect to services and provide a confidentiality report and the attestation report to the services that they can verify that they're actually talking to a trusted ACI instance that's confidential. You can see on the right side, Azure Key Vault with Managed HSM. That's another one of our confidential computing services that we've launched earlier this year. That is built on confidential computing technology, and that's where the keys would be stored. So you've got a confidentiality end-to-end here. What happens is this container instance fires up. It, at test, provides the attestation report to Managed HSM and says, I'm this container, here's my signature and what I'm running. And then there's a key release policy on Managed HSM that says, this key to decrypt the model, only release it if that attestation report comes back with those measurements. And so Managed HSM looks at it and says, okay, yeah, I can give you this key which allows you to decrypt that model. Nothing else can get access to that key, and so nothing else can get access to that model. So now the Azure Container Instance is up and running with that decrypted model protected in the enclave, and now you can have clients that come to it inside the cloud or outside the cloud. Inside the cloud, they'd be inside of confidential virtual machines or container instances. Outside, they can be on your own infrastructure. You establish a TLS connection with that container instance, verify the attestation report. If it passes, then you can start to give it your sensitive data, knowing that it's only going to be seen by that model inside of that container. So let's go see a demo of that in progress. And here you can see I've got container instances. There's 3 images in there, those ones that I mentioned, the Triton server, the encrypted sidecar. Here's the policy that says that I'm only going to release keys or make connections to a container instance that matches this format. What you would do before you deploy is generate a container policy off of a hash off that policy that represents exactly what you trust. And that hash you can see there. That's the model, what the model does that we're going to be using is just does a classification of birds. And now what I'm doing is connecting to that Azure Container Instance, and I'm saying I'm only going to connect to it if it returns this data. So the client is taking that hash, it's going to connect to that inference endpoint. It looks at the attestation report. First thing it does is sees, is it signed by S&P, by AMD's hardware? If so, then I can trust the hashes, because it's the hardware saying this is what's inside that enclave. And then you can see that that hash and that signature matches what I'm looking for, which is the security policy hash, which includes the hashes for the container images and the policy it's enforcing. And then you can see that I released the image to it, it came back and said, yes, it's a vulture. Now, if I modify the policy at all to say, hey, I'm expecting an inference container with a different policy via its hash, you can see what the client does is checks, says, yes, it's an SMP report, it's verified, so I'm going to go take a look further to see if the policy hash matches. And the policy hash doesn't match what I'm looking for, so that's not the container images that I trust, so I'm not going to release the image to it, and that way I keep it protected. So that is available today for customers to use, and we've got customers that are today using confidential inference as well as confidential machine learning capabilities on top of confidential computing. Like I said, what I'm showing you here looks kind of exotic. Hey, this is a flow that we normally don't follow, just like TLS looked 15 years ago to a lot of people. But this is the future. Everything is going to be doing this in the next 5 to 10 years. And that's why we have this vision of Azure being the confidential cloud. Now, the next thing I'm going to talk about is an even bolder vision of the future, and that is quantum computing. So with quantum computing, the idea here, and I'm sure a lot of you have heard about this, we've got classical computers that have great algorithms to process complex problems, but when it comes to modeling the real world, the physics of the real world, the only way to do it really efficiently and solve some of the biggest challenges is to actually do it with something that operates like the physical world. In other words, operates like the quantum world, which is really the way the physical world works. where you've got concepts like superposition and entanglement happening in the real world. And this is the way to solve problems in a short amount of time that would take thousands or millions of years on classical computers, including the most powerful classical computers we could envision, actually, over the next few decades. Really problems that are impossible to solve without quantum computers. Some of the examples here are shown on the slides. Solving world hunger. We can do that by creating energy-efficient fertilizer. Today, creating fertilizer consumes a tremendous amount of energy and produces a tremendous amount of emissions of greenhouse gas. And so if we could figure out how to create a fertilizer that could bypass that, we could feed a lot more people a lot more easily. That's one example. Reversing global warming, there's a few problems here that quantum computers could help with. One of them is creating a catalyst for carbon capture. So actually being able to produce chemicals that would pull carbon out of the atmosphere. That is within sight of solving with a quantum computer. And the problems go on, like clean water, being able to create a photo-activated catalyst to extract materials, particulates out of the water. That is also something. So the number of problems here, there are dozens of problems like this that a quantum computer, once we have it, could just go and solve for us. This is why it's going to be such a turning point for humanity when we have a scalable quantum computer that can solve these problems. Now the challenge, though, with these problems is that they require millions of physical qubits to solve. Millions. And I'm sure you've been seeing quantum computer announcements come out that are much smaller than that. They're big, bold breakthroughs. Hey, big announcements. We've got a quantum computer of this size. They're nowhere near the sizes that we need to solve these problems. And if you take a look at the different types of qubit technology that a lot of these quantum computers are being built on, they all have trade-offs. Because what you need for efficient quantum computers, you need resilience, fidelity. You want them to be stable. You want them to be fast. In other words, the processing of the quantum computer, the quantum qubits transitioning states and you being able to measure them has to be extremely fast to be able to solve those problems. And you need them to be small. And the reason you need them to be small is you need to, of course, create these computers with millions of them. And if they're large, millions of qubits are going to take a computer that's the size of this room, which creates all sorts of problems. How do you synchronize a quantum computer across this kind of distance? And if you take a look at these qubit types, like silicon photonics, photons can be at room temperature, but the detectors need to be at less than 4 degrees Kelvin. Further, synchronizing photons across this room means that you need wires that are compensating for the length and the distances. 1 qubit over here versus 1 qubit way across the other end of the room need to have the same distance for those photons to travel for them to be synchronized. So that is a massive, hard engineering problem that really nobody's really tackled. When it comes to superconducting qubits or transmon qubits, they're large. They're millimeter size. So again, you're talking about millions of millimeter-sized qubits. Again, you're going to have a very large quantum computer with all of the synchronization problems I mentioned. And not to mention that, if you try to shrink them, they become unstable, even more unstable than they are. So there's another trade-off there. And then finally, with trapped ions, or quantum dots, for example, spin qubits, so far there have only been small systems made with them, and they do decohere, or remain stable, for just under 400 microseconds, so not long enough to really do computations without massive amounts of error correction and retry, which makes them non-scalable. And then finally, the trapped ion ones, they're extremely slow, and their gate speed actually decreases as you increase the number of ions. So as you increase the number of ions, they get slower and slower. So they've got a scaling problem that makes them too slow to, we believe, to be practical. So these all have like fundamental trade-offs in that trio of requirements to create a million-scale qubit computer. We believe that there's one promising technology for creating a scalable quantum computer, and that's a topological qubit-based computer. They check all three of these boxes. They're reliable, so they're topological because we can create braids with them that actually stabilize the qubits and keep them coherent for very long periods of time. So what that means is that you can create a computer with far fewer physical qubits because you don't need lots of extra qubits to do error correction. And you don't need to reperform computations many, many times because the qubits are stable long enough for you to be able to perform the computation reliably. There's no sacrifice on speed either. They're extremely high performing. And there's no sacrifice on size. These are micron-sized or nanometer-sized qubits, and so you can pack 1 million of them on a wafer. So we believe like this is the nirvana here for a scalable quantum computer that addresses the 1 million qubit kind of scale problems. And we have been on this journey now for topological qubit, which is based on something called a Majorana fermion. Majorana fermions were something that were predicted by Enrico Majorana back in the 1930s, an Italian physicist, never proven to exist. Only in theory were they known to be possible. So we've been on a quest because topological qubits based on Majorana fermions, the holy grail, yet nobody's ever been able to see one and prove that you can actually make them. We had an incredible breakthrough earlier this year, we announced in March, which is we created a device here that you can see a picture of to create a gate or create a Majorana fermion and prove that we actually did it in reproducible, reliable experiments. So this requires creating what's called a topological phase and a Majorana zero mode. This is the fundamental building block for a topological qubit. So tons of engineering work left, but the question of can we make a Majorana fermion, which is the basis for a topological qubit, is now something that we've passed. So major, major milestone in our quest for the scalable quantum computer. And yeah. So we've been working across everything from CMOS, cryogenic CMOS, which I've talked about before, to control a quantum computer at these kinds of massive scales very efficiently. We've been working on a SDK. The next step is the first topological qubit, so stay tuned for that breakthrough, because that is like the key breakthrough. Once we have a topological qubit, the rest is easy. So I want to close with one thing, which is not really an innovation, but I thought I just have to show it. How many people saw me play Tetris? I posted a video of Tetris on a giant virtual machine. So if a bunch of you have. So for those of you that haven't seen it, what we've been doing is creating larger and larger servers, specialized servers for SAP HANA workloads. As their enterprise customers come, they're bringing their SAP databases, and they're larger and larger. Just to give you an idea of how this journey has progressed, back in 2014, we created something we called Godzilla. It was so big back then, 512 gigabytes of RAM. Still, not big enough for the largest SAP workloads coming to Azure. So we created something called the Beast, 4 terabytes of RAM. Still not big enough. So we created Son of a Beast, or Beast v2, 224 cores, 12 terabytes of RAM, still not big enough. So that video that some of you saw was on Mega Godzilla. By the way, I'm the one that makes up these names. Mega Godzilla Beast, 420 cores, 204 terabytes of RAM, still not big enough. So we're announcing Ultron Mega Godzilla Beast. This thing has 832 cores of RAM. That's what it looks like on the inside. And then, of course, here's me playing, not Tetris, because I thought that's boring now. Here's the program that I wrote that actually pegs the CPUs according to a grid, like a bitmap display, and playing Pong on an 832-core virtual machine. This demo cost $10,000. So I hope you like it. So with that, thank you very much. It's great to be back in person. I hope you enjoyed it. I wish I could show you a lot of the things that I wasn't able to show you, but next Ignite, look for more. So I'll see you then. Hello, hello. Oh, one last thing. I've got a copy of Sysinternals that Scott and I were supposed to give out yesterday, but we forgot because Scott forgot it. Blame it on him. So, question, like, who should get this? I'm going to throw it. No. Let's see. Anybody name, or whoever yells the month and year that Sysinternals went live. First one. Month and year, Sysinternals went live. Close. Colder. No? I think I heard it. Yeah. Nobody's gotten it. You're all around it. All right. This isn't going to work. All right. It was September, by the way. Let's see. What's another? Oh, the name of my co-founder on Sysinternals. Nope. Oh, he'd love to hear that one. That's not it. That's it. There's the book. Bryce Cogswell, who I founded Sysinternals with, worked at Microsoft until 2010 and then retired. So, congratulations. All right, thanks everybody.